So far in this chapter, we already studied the basics of risk measures and spend some time on a very important risk measure called value at risk, VAR. Uh, in order to understand VAR, you just need to draw a picture of the PDF or CDF. It's something similar. Okay, so hypothetically speaking, this is assume this is a PDF of some risk. Okay, and VAR is nothing but quantile. And since we model directly for risk, so to an insurance company, the biggest loss comes from the right tail, right? So the bigger the X, the bigger the loss to the insurance company. And obviously, the company cares about those very, very significant losses. So let's say this is the cut line, okay? On the left-hand side, the size of the loss is somehow manageable to the company. Let's say not big enough to make the company run into any cash issues. But on the right-hand side of this cutting line, the size of the loss is very, very significant and could cause some financial distress to the company. So this part is the right tail, of the loss to the insurance company, and the further you go on this tail, the bigger the loss to the company. Usually, what you do is you assign a probability, okay, and obviously you assign a relatively small one. Let's say here you assign 1%. If you assign 1% for the tail, left-hand side you will have 99%. So this point is what we call the quantile at 99% of this random variable x, which is exactly the definition of VAR is 99% of x. Okay, so this picture pretty much says everything you want to know of VAR, right? But of course, here this is a continuous random variable, so there's no jump. But if you add jump, it's the principal idea is still the same, right? You want a number that is going to separate the entire distribution into two parts. Okay, the tail part is truly the worst scenario to the company, and in this particular graph, I assign 1% to the disastrous scenario. Okay, and then there will be a number that separates everything into 99% and 1%. That 1% is the disastrous zone. Okay, so to recap, VAR is nothing but a threshold, right? But obviously, it's a very simple risk measure, and it was once upon a time the industrial standard. But of course, there are many issues. Let's use one example to somehow discuss the possible drawbacks and motivate why we want to introduce another important risk measure called tail value at risk, TVaR. Now let's look at example 5. So here we consider two random losses, X and Y. I put this very special setup so that the X actually has a single probability mass at its maximum. So X has a maximum point at 1000 with probability 5%. Okay, so X is a very special distribution. It's possible that I apply policy limit, and I assume 1000 is the maximum covered loss. Then it's possible the actual loss may be beyond 1000, but since I'm capped at 1000, whatever the tail is 5% to me. And then I look at another case, Y. Okay, Y has something similar to X, that is 1000 point is also the separation point, such that on the left-hand side of 1000, I have 95%. On the right-hand side, I have 5%. Okay, but unlike X, on the right-hand side of 1000, Y is continuous. Y follows this special uniform distribution. So this U stands for uniform. Okay, so now if we apply the risk measure of Y and we select this special level 95%, it's very easy to see that both X and Y will lead to the same Y at 95%, which is 1000. Right? That is exactly why I set this up. Right? Somehow, I assume, okay, that is the case. And of course, now if we apply Y as the risk measure, we would conclude both have the same risk measure, 1000, meaning there is 5% chance that the loss is at least 1000. But since we already know everything about those two risks, right, we can say a lot more. Right? We know for X, 1000 is the maximum. We have 5% at 1000, but that is not the case for Y. So if you are the insurance company, which one is somehow the better scenario to you? Right? So obviously Y is better, right? Because excuse me, Y is worse, X is better because X, if you insure a policy with risk X, you know that you will have 5% chance to pay a claim of $1,000, but there is no way that you pay more than 1,000, right? But on the other hand side, if you underwrite a policy for Y, you also know that the chance that you will need to pay beyond 1,000 is still the 5%. Okay, the percentage is the same, but the amount is not, right? So here we know greater than or equal to 1,000 reduced to 1,000. This is the case for X, but this is not the case for Y because now we know it is equally likely any number between 1,000 and 5,000 will come up, right? So once you know the claim is more than 1,000, it will be any number between 1,000 and 5,000, right? So obviously you don't want Y, right? Because it's likely that you may even see a claim as big as 5,000 or as big as 4,000, anything in between, right? Is possible. So in this case, we would say Y should be more riskier than X, right? So, but that is not reflected in this if you apply valued risk, right? So in this very naive example, we see that Y may not be good enough to tell us everything, right? Because we not only care about the threshold, we also care about how worse we might get on the further tail part, meaning for a claim bigger than the threshold, right? So that motivates us to study the risk measure in this video. A little bit more discussions is, of course, in the definition of Y, this level is very important. We know it's always between 0 and 1, right? And Y gives the worst 1 minus delta scenario. In the previous graph, it's going to be 1%, the worst 1% scenarios. So in our example 5, we already saw that with delta being 95, we can't see any difference between X and Y. But if you pick a different level, let's try 99. The Y of 99 is still the same, right? Because we have 5% at this level. So the Y at 99 is still 1,000. But Y at 99 for Y is not 1,000 anymore. It's actually 4,000. Right? The reason is because beyond 1,000, we have a uniform, right? And uniform account for 5%. Now we want the number that gives us 80% of the tail part. That's exactly 4,000. From here, we easily see because 4,000 is greater than 1,000, right? So we can claim Y is more risky than X, right? But however, we in general, we don't know, right, how to pick. Okay. By the way, this is a question I didn't mention. When when we will studying the topic of VAR, right? It's more of an ad hoc, right? So we studied usually 95, 99, or even 99.5. But why? Why do we pick those numbers? There is no scientific reasoning behind it. Of course, we can say we really care about the tail, right? But why 95, not 96, right? Why 99 instead of 98.85, right? So it's of course, you would say those numbers are nice, but some may argue, why? Why don't we pick something else? Why don't we use more decimals, right? In general, we don't have a good reason. It's except that those numbers look nice, right? So with that in mind, since anybody can pick any delta, right? In order to get a more consistent ranking of risk, we need to come up with something better, right? Better than VAR. So that motivates us to compare the average of VAR. So previously, we only consider 1 point, like 1,000, which is the case for both N and Y, right? Or if it is 95, okay? Or it could be 99, then for X is 1,000, for Y is 4,000, right? We can continue, right? We can continue for any number, like a 96, 97, in the end, what we want is we want to average all those numbers together to see which one is bigger, right? Because here, even by eyeballing, we know that the average in the case of Y will be bigger than the average in the case of X, right? Because there's no averaging effect on X, it's always 1,000. But for Y, as the level gets bigger and bigger, this number gets bigger and bigger, goes all the way to 5,000, right? So if you average, it will be some number between 1,000 and 5,000, meaning it will be bigger than 1,000, right? So we get to the result we want, that is Y is more risky than X, right? So with everything in mind, let's formally introduce the definition. Given any delta between 0 and 1, the tail value at risk, TVaR, of a random loss is given in the box, okay? So what we want is not only we care about this threshold, right? We actually want to know beyond this level, what would be our average size. So previously we only, so if I go back to my graph here, previously we only care about this point. Now I want to know everything within this range. So I want to know what will be the average. Right? I know this VAR gives me the separation number, gives me the threshold. Everything I consider will be beyond or on the right-hand side of this VAR. Now I want to know the average. Right? So in order to know the average, I would need to know how this tail is distributed. Right? So I don't care about this part. I don't care. But I really want to know my tail distribution. Right? Because in the end, in terms of risk management, tail distribution is pretty much everything, right? We don't care about small risk. We care about big loss. So that's why this is still very easy concept, because I assume we already have some understanding on conditional expectation, because in the end this gives us a number, right? Of course, it depends on the condition, right? It should be a function of this condition. But nevertheless, right, we pick special delta. Once a special delta is chosen, this number is given, right? That's why I call this a number, because in general, conditional expectation is a random variable, right? It's a random variable of our condition. Since usually we specify this condition, you get a number, right? So in the end, we consider the entire tail, but we still want to use a single number to give us a quantity of the riskiness. That's why TVaR, although is a huge generalization, it not only consider a single point, it considers the entire distribution. In the end, it still gives us a number, right? That's why, it's nice, right? We don't want to consider at different deltas. We just want to pick a delta, and I want the measure to return me a number, okay, instead of a vector. I don't want vectors. So here, what we can tell is TVaR is actually the expected loss given everything. So given the loss should exceed this quantile. Okay. There are many different names. Here I use TVaR because that is the standard notation used in the textbook, and I believe it's also used by the SOA reference. The book written by Krugman, Pania, and Wilmot. They also use TVaR. So that's why we use TVaR. But it's likely that you will see other names, like a conditional tail distribution, expected shortfall, or conditional value at risk. For instance, I usually use this because to me, this condition is the best. It's because it is conditional expectation, right? Or this also reflects the idea of conditional, right? Because we do have a condition. But of course, tail is also a good name because we care about the tail part. We want to know the tail distribution, the average of the tail. So all of them make sense. So throughout this course, we will stick to this name, TVaR. Okay. I also want to mention one important thing is in the book of Say, he actually defined the TVaR as this. He defined TVaR as the difference between TVaR and VAR. As I highlighted in red, this is very non-standard notation. That's why I put we do not use this. So this is the only time you see this. I will never use this again. I simply want to emphasize this because usually people treat TVaR the same as TVaR. Okay, it's not the difference. I have never seen the difference other than this book. So please do not use this definition. Cross it out. Okay. By the way, in definition 8, everything works well. If x is continuous, but if x is either a mixed or discontinuous or discrete, strange things may happen. We will come back to that. But now you can kind of assume we are in the continuous random variables domain because when we study risk measures, usually we study for individual risk, and the individual risk is usually modeled by, or claim severity is usually modeled by a continuous distribution, right? But of course, we can have discrete points due to different modifications. Definition 9 is actually more meaningful, okay? And it's likely the one we often use to calculate TVaR. And here I start with this. Assume x is continuous, okay? Given delta between 0 and 1, I have this. This has more meaning because I can directly say now TVaR is defined as the average of all VARs between delta and 1. Between delta and 1, meaning I'm looking for this part, right? So assume, right, on the right-hand side is 1. So I only look for VAR that is between delta and 1. And I'm trying to do the average because I'm doing integral and divided by 1 minus delta. So what I have here is average. So on the right-hand side is the average of all VARs that is located between, for the level between delta and 1, right? The bigger your level, the further you move to the right-hand side, okay? And we want to average over all those quantiles, okay? That's why, this one has more actual meaning to us. The previous one is more mathematical because usually, conditional expectation is a more advanced concept, but everybody understands integral. right? And when you integrate, you kind of do the average, okay? Here I give you a short proof. I quickly mention because the proof itself is not important, right? You can directly see the meaning from here. So that's why proof itself is not as important as this intuitive understanding, right? Intuitively, it's right hand side is just the average, and that's enough to us. If you really want to know why this is the case, we start from the definition 8. This is definition 8. So far, this is how we define TVaR, right? And by definition, it's a conditional expectation. So you go from the condition to infinity. I mean, it's possible that there's a maximum for your x, but I don't care. I just write infinity. And in order to calculate the conditional expectation, you will need to figure out the conditional density. That is the non-conditional or unconditional one divided by the probability of condition, right? So that's the definition. From there, we need to do a change of variable. That is to use y to replace the CDF. That's somehow complicated, right? By the way, from here you can see dy equals right? So it replaces this part. Okay, but it's not that straightforward to figure out the interval. Although again, by intuition, right? So this number corresponds to var delta is x, right? One, if there's no up limit, this is infinity, right? So that's why it expands from here to infinity. It corresponds to delta to 1. And this PDF dx equals dy, which I just showed here. And the bottom is 1 minus delta. That is obvious, right? Because that is the condition, right? That is the condition. So this part has probability 1 minus delta. So that's it. And from there, we know this is 1. Right? The inverse of your CDF is quantile. Quantile is 1. So that's why I can write it as 1. Take the constant out, then I get this proof. Okay. Once that is done, let's do some exercise, and then we will close this video. Okay. So the first one, my x is exponential. We already did the var for exponential, so I first write down the var for exponential. By the way, since for part A, x is exponential, there's only one x. I don't want to write x, as the argument, so I just save a little space. So we derived this result in the video of var. So if you forgot, you can go back to view that. So now, so let's change this to y, put dy. Okay. So it's a very easy integral, right? I mean, if you want, you can even use another change of variable to replace 1 minus y. So you get this 1 minus delta. Here's 0 log of y. Then you have the negative y. Then it will cancel this, so it becomes positive, right? So from there, you can easily get the result. So this will be y log of y minus 1. By the way, you do need to apply integration by parts to get this result. But I assume that's not an issue by now, right? So put everything in. You will get negative 1 over lambda times log of 1 minus delta plus 1 over gamma. Okay, what is this? This is your y. So I have Okay, this is a quite interesting result. Later on, I will give you a result about this. An immediate observation is lambda, of course, is always positive, right? Um, so, right, I mean, this is not surprising, right? Again, what is the definition of TVaR? TVaR is the average of all VARs that is bigger than VAR at the given level delta. Right? Is average of everything that are greater than the sky. That's why the average is supposed to be greater than your threshold, right? Because it's everything on the right hand side, and you do averaging. What's more interesting is this number, right? So later on, we will have a result. In most actuarial science books, they don't derive, so that's why I don't put too much attention here on the relation between this and this. The second one I'm going to skip. That's because we don't actually have explicit results for the log normal. By the way, this is the log normal. You somehow use notation. So if you want, you can look at your textbook for the expression. Let's do this. This is more complicated. So we also solved for the VAR of Pareto. So this is a standard Pareto distribution. So let's do TVaR. So let me first copy what we already derived, meaning the inside part is the VAR at level y, dy. Okay. Here we want to solve this integral, right? And it's rather complicated, right? So there are a few things we can do. You can directly replace this. You can directly replace this, or you can do it step by step, meaning you can first use something to replace this, right? And of course, you will need to differentiate to see what you have. You will need to do the differentiation. So let's take. So from here, what we have is if you take negative alpha, raise the power to negative alpha on both sides. Right. So this might help you more to work with what is dy, because now I see dy is negative alpha will come out, then it will cancel the negative sign. It's alpha. Then the original power has to be reduced by 1. So now, okay, those are my scratch work. Okay, it is 1 minus delta to negative 1 over alpha. And because alpha is greater than 0, so 0 to negative power is infinity. Then inside I have gamma u minus 1, right? Replace the whole thing. Next, I need to replace dy. Right. Okay. This is a much nicer form. You can take every constant, all the constants out, and take a look what we have now. So what we have u to negative alpha minus u to negative alpha minus 1. Right. So both are power functions. Right. So now it's very easy to solve this. For instance, this becomes u negative alpha plus 1, and then you need to divide it by negative alpha plus 1. Minus becomes plus, and then u to negative alpha, and because of the negative sign, it becomes 1 over 1 over alpha, right? Then you put everything in. Let me give you the final result. We will have, this is alpha gamma divided by alpha minus 1 times 1 minus delta to the order of, let me erase this. I don't want you to get confusion with the power term. But as you can see, the antiderivative is very easy to do. So where am I? So here. So the power is -1 over alpha minus gamma. Okay, so that is the result for Pareto. Let me end here for this video. In the next one, we will continue the discussion of TVaR, but for slightly more complicated issues when X may not be continuous. Okay, I already mentioned strange things could happen. So in the next video, we will deal with those.